Okay. Fantastic. Okay. Well, thank you everybody for attending this Institute for Data Science and Artificial Intelligence seminar series. This seminar series is supposed to showcase the enormous, the wide-ranging themes that the Institute cover. And so we have asked all of our team leads to nominate somebody who is doing some really interesting work related to their theme. And so Leaf invited Sara Schnadt, I should say, to give a presentation, which sounds absolutely fascinating. I'm really looking forward to this. I had a quick look at Sara online. You should have a look at her website, and I think it just really demonstrates a commitment to simplicity and elegance in communication and systems design, and I think it's well worth a look. And it really got me thinking about how in data science in general, there's so much room for creativity, that it is a really creative endeavor. And I think I try to convey that to our master's students on our various programs, but probably not enough. You know, it is really exciting to just make something out of nothing, and you can really get your creative juices flowing. And I think that's a really nice, that's illustrated really well in Sara's work. Okay, so I'm going to hand over to Sara now, who's going to speak for slightly less than an hour on design thinking on Mars, architecting new systems for collaborative science on the Martian surface. Over to you, Sara.
Thank you so much for having me. So yes, I'm Sara Schnadt, and I'm an artist and a designer by training. This is just a diagram showing a little bit of my background. The vertical columns there are decades. So starting in early childhood, studying dance and visual art, and then in my teens, added study of performance art, which I got into in order to combine visual art and dance together. And then later, as I was in graduate school and getting into like some day job work to go alongside my art, I added database design and UX design, and kind of kept also over the next couple of decades to accumulating more and more creative practices as I've gone along, out of interest and curiosity, and really also over time, my work, especially in my day job work, as it were, I've been designing to more and more complex contexts over time. So I started working on a city scale project to provide business and opportunity resources to artists in all of the different arts disciplines for the city of Chicago, for their cultural affairs department. And then from there, I worked on a couple different national civic data projects in the field of digital journalism, one providing election access to journalists for their stories, and the other one visualization tools for using census data in their stories. And then from there, I worked for a data science startup that creates tools for scientists with very large data sets to explore and visualize their findings. And from there, I've been working in aerospace, first at an aerospace startup that images the whole surface of the planet with a network of satellites. And I designed them an interface for exploring that imagery. And then for the last 5 years, I've been at NASA Jet Propulsion Lab, where I've kind of expanded the complexity much more, just because of the range and depth and scope of kinds of projects done at JPL. And that has been really incredibly eye-opening for me, being at JPL. And it's really changed the way I've created a relationship between my work in technology and my own creative work. Up until the point where I started at JPL, I really considered them to be two parallel practices, and that I would use my work in technology to inspire and inform my artworks. And this is an example of one of those. This piece I did, it's called Connectivity, and I did it starting in 2007, right when Web 2.0 was just becoming a thing. I think Life magazine here in the US had you as the person of the year that year, as the new author of content in this newly widely accessible kind of collectively authored platform, which was the implication of Web 2.0. So I made a performance where I built the internet as a performance in a museum space. And I used as a kind of a reference for the structure of it, a visualization that I found by the UPTI project, which had algorithmically tracked the topology of the internet and visualized that. So I used the aesthetic and structural form of that visualization as the reference for the installation that I built. So that was really the way my artwork and my design and technology work functioned up until the point where I started at JPL, where it was part of my research, and yet I was getting paid to do it. So I was quite pleased with that. But then once I started at JPL, I found that I was just so inspired that I could no longer think of that work as my day job. It was just too fascinating and too profound. And so things just really started to change for me once I started at JPL. And when I arrived at JPL, I'm going to tell you about two projects in this talk. The first one is actually not Mars, it's Europa Clipper, which was the project I was hired onto when I started at JPL. So I was hired at JPL to work on the Europa Clipper mission as a UX designer. So that's how I got my entree into JPL, and that at that point was the primary technology practice that I was using. I was hired to be a UX designer for the science planning software for Europa Clipper. And when I arrived, I was just completely awed by the majesty and the brilliance of what was being done on this mission, and just so fascinated by what we were trying to accomplish there. And the mission itself, the goal is to survey this moon of Jupiter and to evaluate if and in what, and kind of characterize an enormous ocean under the surface of the moon, which is a thick layer of ice. And when I started on this mission, in addition to being really struck by the context of the work that we were doing, I also, and I'm not sure if you can see this very well, it really depends on how big your screen is, but I'll talk about it a little bit. I was really fascinated by wanting to understand the people that I was working with, because most of the people I was working with were what JPL calls systems engineers, which is really a kind of person that thinks about how all the different very technical parts of a large system fit together, and also designs how they all fit together, which is a practice that's very necessary for working on projects on the scale of what's done at JPL. So I made this diagram to try and understand the fundamental differences between an artist, a designer, two practices I knew well, and a system engineer. So this was my initial take on it, which is basically that they had different understanding of the problem space, where a system engineer had a lot more technical depth, but a designer understood the user needs a lot more. And that an artist had more of an understanding of this, the cultural and social context of what was being done than either of the other two, but really nothing close to either the understanding of the user needs or the technical context. And that in process, my initial impression of systems engineers was that they used very rote and structured processes, whereas designers tended to have a more versatile toolbox, and artists were completely agnostic to which tools to pick up to solve a problem, and were very, very versatile. And then in the solution space, that as a result of those two other things, artists tended to identify what was possible in a much broader surface versus what's viable, whereas systems engineers would identify a much smaller but more focused range, which there's pros and cons to both, which I thought then mapped to to what extent the three different disciplines could really vision what's possible, as opposed to simply implement in the here and the now things that we know how to do at the moment. And I have to say, I wanted to share this because this was kind of my orientation to coming into this new context. I did, for several reasons, discover over time that this was entirely wrong. And first, kind of initially, right after that, I discovered it was entirely wrong. As part of this initial orientation, I hosted a workshop with a group of designers and systems engineers, and I wanted to understand more nuance about how we were different from each other. So I asked them all to write down the details of their qualities, their processes, and their artifacts. And then the idea was that we'd put them all up on the whiteboard, and no more nuance about how we are different from each other. But then what happened in reality is that we realized that most of the qualities that we had in these three areas were in common, and that we actually might have slightly different words for them or use them a slightly different way, but basically very similar. And we were much more similar than we were different. So that was really interesting as a kind of a starting place for getting into the work. So here's some examples of some of those qualities that we identified that we have in common. They're very similar between design and system engineering. And then since then, and this is actually, I'm kind of saying this retroactively, I didn't know this at the time, but since I've been at JPL for 5 years now, and in the last year and a half or so, what I've discovered is that I'm actually a system engineer, and my title now is actually system engineer. It's particularly these highlighted qualities are the ones that cross over for me between the two. And also my practice as a designer with these highlighted ones makes me a particularly useful systems engineer, that I'm particularly intrepid at solving hard problems and synthesizing together across a complex space as a result of having this design background as well. So once I had this basic orientation of the science we were doing and who I was working with, I then kind of was considering ways of like, how do you immerse yourself in a mission at JPL? And the first consideration, and this is again was fundamentally, it kind of goes without saying, but I'm just going to call it out because it's really present when you start working at a place like JPL, is that. And I also love the movie The Martian. So this is a quote from The Martian, this one scene in The Martian, which I drew because I'm not allowed to actually share a screenshot of the movie. But that all of this work is big, it's beautiful, and it's greater than you, which is true compared to any other work I had done in technology previously, but also is particularly true compared to my individual art practice. That the thing I realized, the thing I love the most about really applying fully my creativity into this context is that I really find that meaningful. Another context that where it's, and I think I'm covering this. Let me see if I can move so you can see this. You are here. Is that the legacy of working at JPL. JPL existed before NASA. They've been doing missions near Earth and then into the solar system, doing missions since the late 50s. So being part of that legacy and being the most recent of multiple missions to the Jupiter area as well is part of the context of the work. And then part of the context of the work too is doing it on site. And of course, in the last little while, there was a couple of years where we weren't on site, but nonetheless, working here at the JPL campus, which is on the edge of Los Angeles, up against the San Gabriel Mountains. It's basically up against its enormous mountain wilderness, but near LA. It's a campus of about 6,000 people who all work there on site, or at least they did before. Now it's kind of mixed, but nonetheless, that's the original quantity. My office is here in this building. This is kind of where I've located it on the campus. And there's a couple of rooms specifically that are most notable about this campus. One is the room on top here, Mission Control. This room is where all the spacecraft beyond the moon that are out there beyond the moon are being communicated to. This room controls that communication for all of the spacecraft beyond the moon. So this is a pretty incredible place, and this is located here at JPL. And then another really interesting room that's here is the high bay, which is a enormous clean room space. That is where we build a lot of the space robots that go to space. I think Curiosity is being built here in this picture. Right now, currently, the Europa Clipper spacecraft is now in that room and is in the process of being built. And that room itself, the high bay, is right next to my office. It's right here. So it's pretty cool. I get to go over there whenever I want and see the progress of them building the next spacecraft, which is pretty exciting. And then lastly, and this is just going to the scale of the work and the number of people working on it. When you're working on particularly a flagship flight project, one of the biggest projects, there's a lot of littler ones going on too at any given time at JPL. when you're working on one of the biggest ones, which Europa Clipper and Mars 2020, which I'll talk about, both are, there's this enormous organization of people collaborating together to develop. So there's the leadership on the top area. Then there's these three primary areas where the design and development process is happening. One is the mission system, which includes basically all of the systems on the ground for running the mission, as well as all the process and operations design. And then there's the flight system for building the actual spacecraft itself physically. And then there's the science system, which are all the people who are designing different science teams around the world who design and build and then run their science instruments that are on the spacecraft. And then within the mission system, there are several different areas as well, which have interfaces to the spacecraft, to the communication network, and then ultimately to the planetary data system, which is the science repository that is then shared with the world after the mission, or during and after the mission, which is the ultimate goal of all of our missions at JPL. So here there's basically process design associated with all the different capabilities I described before. And then there's the ground system overall. And then also within the ground system, there are different capability areas as well. So way down here at the bottom in this one little area is where I started at JPL. And I've since kind of moved up and expanded the scope of my work, but this is where I arrived, which is just by way of like orientation. This was all part of the orientation that I had. So all of these different amazing people that work on a mission, although there are a lot of them and they all have different concerns and areas of focus, there's really just one single goal. And for this one, the goal is to understand what's below the surface of the ice on Europa and see if there's a giant ocean under there, which would be really exciting because it would suggest that the moon is habitable and it could support life. And the design problem of this is really, really enormous. It's like on the scale of collaboratively designing something like the Death Star, which is, I just wanted to put this in to emphasize that. It's as a design problem space, it's just so enormous. And to me, that's extremely fascinating and has been very, very fun to engage with creatively. And it's really this that's gotten me drawn out all of my art interest, kind of drawing it out into this work. And translating it kind of completely into this work as a result of just how enormous and fascinating this design space is. And so pretty quickly, in a few months after starting on Europa Clipper, and getting fascinated with the whole system, I discovered there was an issue that I could help solve on the mission. And that issue became a system architecture project that I developed for the mission. And I'm going to just tell you a little bit about that. So the mission itself has 9 instruments that will be studying the atmosphere, the nature of that ice layer, and then understanding what's below the ice. Especially they'll understand that we won't really be able to dig through all this ice, but there'll be plumes coming up, we hope. And so you can kind of take readings of that water in the atmosphere, as well as do various kinds of soundings and radar and various things into the and magnetometry. There's a range of different kinds of observations being done to understand as much as we can about that water underneath the ice surface. And the challenge of this mission is that, and this is the primary challenge that the mission is designed around, is that this is a really high radiation environment because of the proximity to the sun. The moon itself, if we were to orbit around it, it would just continuously, it would fry all of the electronics on the spacecraft really fast. So in order to protect the spacecraft while still doing the science needed, what the mission design is to do these flybys close to the surface. So if this is Jupiter and then Europa orbiting around, there's this very short flyby of about 4 hours close to the surface, and then there's a day on either side of approaching and then leaving again, and then a 14-day orbit that goes around Saturn as well. and then back to a short flyby again. And that's a really challenging mission design for being able to learn as much as we can from each flyby and then adapt the plan for the next orbit to accommodate any new learning that we had on that flyby. And as a result, the way that the mission is doing its planning needs to be slightly different. So because of working in space, basically, rather than do lots of prototyping for processes and also physical design for a spacecraft and for a mission, what we do instead is we do a lot of mathematical modeling for different design choices for different materials, different placements of different things on the spacecraft, as well as a series of activities that the spacecraft will do, so that we can try out and optimize for a really successful plan and a successful mission in advance. Because once the spacecraft launches and it's out there towards where it's going, there's no do-overs, there's no revisions. So traditionally, mathematical modeling has been used a lot on JPL missions for the initial design of the spacecraft itself. But because of this need for intense agility on the mission, on Europa Clipper, mathematical modeling has been used for the planning process as well, way more extensively than on any previous orbiter missions. And as a result, what I noticed was there was going to be a need to improve the way in which mathematical modeling was managed for the mission. Because in order to just basically prototype with math for the initial physical design of a spacecraft, all of the software and infrastructure around authoring and validating and running the modeling and the simulation previously had been on the kind of in the ballpark of like a very much prototypeware, and instead we needed something that'd be more like production software type environment, much more stable, organized, systematized, things like that. So I proposed a design to basically level up the way that we use models. And the mathematical models are the physical spacecraft and all the different subsystems of the spacecraft, as well as of the different science instruments on the spacecraft. So basically what we need to be able to do, and this was new and much more demanding than on previous orbiters, is every time we fly by, in that time in between, actually understand exactly what the difference is between what we thought was going to happen and what actually happened, and then update our plan based on what actually happened. And in some cases, even update the models that we're using based on what actually happened. So in order to do this design, I relied a lot on my design skills and also my just drawing. I did a lot of drawing on this mission, obviously, as you can see. And I'm just showing a couple different versions of drawings here. I did a bunch of drawings to just understand the nature of the problem space for designing this architecture. So on the left is my understanding of the full planning cycle. That previous diagram showed just what did we think would happen with the plan, with this little visualization being kind of representing the plan versus what actually happened. And this is just a more detailed version of what the different parts of the system are that are part of that simulation, planning, uplink, downlink trending, analysis, and comparing with previous understanding, and then integrating back the learning and updates into the modeling to go back into the plan. And then on the right here, I have got just a whole ton of different considerations for the design itself, ranging from things like should the modeling process be a black box to the user or not? That's when it was one of the big design questions. And then some different qualities the architecture need to have, and then some design tensions, like how heterogeneous can the models be, and have the system still tolerate them, for example. And then once I got into the kind of the definition of the system piece, I did a lot of drawing as well around different considerations for the design of the system. How many interfaces did it need to have? Should there be a central hub where all the models live? that's hosted and managed, or should they live where they're authored in the science teams repositories, in the spacecraft subsystems repositories, and then should the system go and call them where they live and run them from there? That was like a fundamental design question, things like that. Also, the models themselves have a lot of different facets to them, including things like the fidelity, which makes them run faster or slower in the simulation, like how precise they are. And there was a lot of different kind of facets to the models as well. A fundamental challenge for a process like this, which was basically solved by a lot of human elbow grease previously, and just checking and rechecking and QAing and writing a lot of weird custom scripts. Fundamentally, usually the people who have the subject matter expertise to describe with math the different behaviors that need to go into the simulation are different people than the people that know how to write code around that math to make the model actually function effectively in a software system. So that was a fundamental challenge for this design as well. And then what I ended up coming up with, and this is very high level overview of it. I can't show you the detailed one just because it's not something that could get cleared. But basically what I came up with was a solution that would help all the various people, whether they were knowledgeable about the software around their math or not, to upload their models into a common service and then run draft versions of them to make sure they were behaving as expected in a common environment, and then finalize them after they could see that themselves, that through the system, that their models were actually behaving accurately, then finalize them and then deliver them to the simulation process. And here's just a detailed version of kind of that workflow. This is really kind of a diagram of that use case primarily, where the model management system has a service that delivers the right models. Depending on what part of the plan you're simulating, you can either deliver them to these sandbox areas that the team can use either independently for their own models, or in interaction with other people testing out their own models as well, because there's a lot of interdependencies between the different parts of the spacecraft. Like, for example, if one instrument to do its observation, if it's an atmospheric instrument, might need the spacecraft to be doing this rolling movement in order to just scan and collect material from the atmosphere around the spacecraft, where there's another instrument might be photographing the surface at the same time. So those two activities can't happen at the same time, for example. And there's many different interdependencies like that. They're also incorporated into the simulation. So they can run test versions with their updated models in these sandbox areas. And then once they know things are working as expected, both in isolation and in interaction with others, then they can update them and put them into the primary planning area to be used to update the simulations. So that's the overall design that I came up with for the mission. It was a really exciting process. I got to collaborate with many different kinds of people and iterate through the drawings I did also in this process. As I was learning the domain, they function very much as what we call in design a boundary object, to make sure that I was on the same page with my subject matter experts by drawing out what I think they meant and then validating it with them. There was a lot of drawing that happened in this process, less so on the second architecture project, because my capacity for understanding the domain increased a ton from the first project to the next. But then it resulted in this design, which was mostly used to feed into another multi-mission simulation project that happened. I wrote a whole ton of requirements for the system that were then fed into another solution. So it was really kind of an interim study that this project served as, to help the mission understand to what extent this was a risk for the mission itself to have this level of rigor for their model management. So then this project I did for about 2 years. Like working on Europa Clipper and then working on this project I did for about 7 months, but then I was doing a bunch of research leading up to it. And then after that, I was invited to join the Mars 2020 mission. To design an architecture. So I was actually hired. That first one was speculative. I proposed it and I kind of transitioned myself from a UX designer to a system architecture over the course of that work. And for this one, I was actually invited to make a new design and brought over to the mission to do that. And the design that I was invited to do was around capturing of science intent for the science team. So a bit of context about this mission. And this is the system that I designed, and then also I oversaw implementation, and they're now using it every day on Mars. So that's super exciting when to get to that point. The objective of the Mars 2020 mission is to, and we landed on Mars about a year and a half ago, and have been executing this mission since then. The goal is to identify opportunities for and to acquire rock and soil samples to bring back to Earth, which is the first mission that's actually done that, to physically take samples of the surface of Mars, and then in subsequent missions, they will be bringing the samples back to Earth, which will be very exciting. But the goal of this mission is to actually identify those samples, which is a real big challenge, because the area that we're in, which is the Jezero crater, it's about 100 square kilometers. So every time we choose one spot to say, oh, let's take a sample here, the opportunity cost for not taking a sample somewhere else is enormous. And the whole science team needs to kind of really think carefully every time we take a sample, as well as thinking about even where we're going to survey the area to understand where we could take a sample to know what would be most interesting to bring back from Mars. We are in this delta area of the crater, which is kind of a giant river mouth, former river mouth. So that is a particular, and we identified ahead of time that was an ideal place to be. But even still, the amount of ground you could cover, and there's only so many, there's like 24 samples that we can take overall. So really making careful choices is a big part of the mission. Also, there were samples done on the previous mission, not to bring back, but just to kind of analyze on the spacecraft. And the number of samples that are expected to be taken in a short amount of time is basically like double the efficiency of any previous mission. So just more science, faster, smarter, basically. So as a result, the science team wanted to change the way they or improve on the way they're organized about making science decisions. And the idea of science intent of like, why are we taking this sample? And are we all aligned on why we're taking this sample, or why we're doing this observation towards potentially taking a sample? The way in which that kind of rationale was defined and also communicated previously was a lot more informal, and mostly through human interfaces, through people getting together and talking, people being in one planning process, and the same person then being in the next day to share what everyone was thinking the day before, things like that. So the goal, and this was a desire of the science leadership of the mission, was to create this new design that would formalize that more. So the strategy that we had for this architecture was to basically facilitate alignment of the science team around the objectives of the mission, or to improve this collaborative decision making and help everyone be more efficient and strategic. And the solution that I came up with in collaboration with folks from the science office and science operations leadership was to create a cross-cutting software architecture that links these science objectives to in each of the campaigns that we're doing, which is a kind of a large area of planning on the surface, to all the pertinent planning and analysis tools that they use in their workflow for both kind of the planning side as well as the downlink analysis feeding back into planning, so that those science rationale are just simply there embedded in their tools, in their process throughout, to create that accessibility for all of the team. So the goals of the architecture itself that I defined together with the science team is this decision-making one that I mentioned before, which also really helps with the observation design when the rationale is there in advance. When we're on the tactical shift, and the folks who are designing an observation, they can see in their tools why we want to do this observation. It helps them actually design the observation as well, which is really, really handy. As well as the interface, like the planning interface, sol to sol, so that if it's not the same people on one day and the next, the science team who are dialing in from around the world to decide on what we're going to do, and also the science operations folks, they can see why we wanted to do this observation today. They're in the tools. There's a central tool, which I'll show briefly in a minute, that functions as a tracking tool. So you can basically see our progress in each campaign area in terms of the science intent. And then these same kind of science rationale statements are also associated with the data that comes down. So they function as metadata on the images and other science data products that are derived from the observations. So then they're also part of a kind of a searchable archive of the mission. And we're actually, as part of this PDS, the science data that's delivered to the public, this metadata is now being delivered as part of that as well, so that context is there with the science products that are made available to the public and for research. So I have a lot of pictures to show you. There's just a few more minutes, and it won't take that long. After a couple of a ton of bullets, just to kind of give you a bit more sense. So the thing that I realized that could be really useful for this design, given the needs of the science team, was to actually borrow an approach used in software engineering for helping large numbers of people collaborate together in a non-prescriptive and iterative and somewhat improvisational way. It's called agile software development, which some of you may be aware of depending on your exposure to software processes. I had lived through that transition from what was previously called waterfall, where you plan everything in advance and then you just execute it in a linear fashion, to agile, which is a fundamental shift in the way software is development. I lived through that in my previous experience in software, and I recommended to the team that we borrow that whole approach for this and just translate it to this context. So rather than having epics and stories, which are the concepts that are used in Agile for defining kind of like a goal for a plan, like a big plan, and also the different building blocks of the plan that enables a lot of versatility in the actual implementation of the goal. We came up with these words, goals and tasks, just because they were a little bit more resonant for the science team. But they function really in the same way, where there's a high level objective, which is the goal, and then there's a task, which is a very specific set of observations that will investigate the goal itself and can also be used for observation design. And the way that these function, and there's basically 3 levels of planning process: one that's on the level of the campaign for about a month at a time, one that's about 5 days in advance of tactical, and then one that's on tactical. And unlike with the orbiter planning for a Mars surface rover, every single day you're learning new things that come down from the end of the day on Mars that you want to apply the next day. So it's a very quick turnaround of being reactive and responsive to what's happening, while at the same time you want to be aligned with your broader strategic goals at the same time. So having all of these science rationale in all the tools help the people who are working the planning at these different scales to stay aligned and to be learning from what's happening day by day and folding that back into our understanding of the goals and the tasks, as well as having the kind of the downward guidance as well, making sure that the folks on tactical aren't basically going rogue from what the broader strategic goals are on a day-to-day basis. So that's how this design works in this way. Then I just described that, so I'll skip this. So here's this architecture. Basically, when I came in like a year and a half before launch, the different subsystems of the team that do all the planning and the downlink tools had already mostly built their systems. So what I did was I made a design that overlays on top of the existing ground system architecture and leverages it for this purpose. So there was already these existing tools for exploring kind of from an orbital view, the surface of the planet, this tool called CAMP. There's another one that's a surface view called Astro, which basically kind of like Google Maps and Google Street View kind of thing. And then I built a tool for, it's basically like the Kanban board from Agile of tracking, writing and then tracking the progress with the goals and tasks. And then there's a tool that's used for building the plan. And then there's also a tool that's used for exploring the images that they came down. And this architecture in essence, which is described over on the side here, it shows up, it creates associations based on the backend databases of all of those tools to the goals and tasks from each one of these kind of backend databases for these tools, and also has interfaces where you can assign and view and search on the science intent from the different tools as well. And I'm just going to show you real quick how that works, because I have images of all the tools. So here's CAMP, here's that orbital imagery one. So here's the Octavia Butler landing site. So this is the tool that they actually use for the campaign planning primarily. And here's like the rover path. And for each strategic area, there's a list of goals. So the actual goals for a campaign are assigned here in this tool, whilst the team is actually looking at the orbital imagery. And then they can, once they're assigned to a campaign, then you can start writing tasks in our tracking tool. So you can see this does look like a Kanban board with the to-do, in progress, and done, which is a basic idea of a Kanban board. So the team can quickly see how far along we are in that campaign, and then write the tasks that go with that goal here. And then as we go along, there's also detailed observations that have gone with a task that shows which sol they're on, and that they have an activity name and then a specific target on the surface. And then as the activities are executed, you can also link through to the other tools to see the data products that also have that science intent. So this tool is very powerful for keeping track of everything we're doing based on the science intent itself. And then here's the tool that's used for building the plan. These little rectangles in the middle are on a timeline, basically all the different activities that are being done that are then uplinked to the rover to execute the next day. And as part of that, you assign the science intent to each one of these. These are the science instrument activities here. This is one of that science instruments, for example. And then on the downlink side, there's a tool for exploring all the imagery that comes down. And here, when you see an image of an observation that's being taken, you can see its science intent there with it. So you can see, as you're looking at the image, why did we take this? And then there's also one other part to the architecture, which is keywords that are basically used on the downlink side to characterize the different features. And so there's a consistent taxonomy that has been developed by the mission archivist that's also in our tool that then is linked to MarsViewer for assigning keywords to the features that are seen, which in future could also potentially be used for feature machine learning feature recognition, be kind of the building blocks of that, which would be great. And then there's also finally another tool that the mission archivist maintains with the best picture of every rock that we've observed, and then the metadata and characteristics of that rock, and the keywords are linked through to this tool as well to be used for describing consistently over time all the different features. So that's this design. It was an absolute thrill to get to collaborate with the science team and also with the subsystems, the software ground subsystems, to realize this design and build it out and implement it in operations. I also got to be in operations for 5 months and observe its use between the different planning processes so that I could tweak the design and make updates to it, and just see it really working for them, which has been really a delight and an honor. And really that's where I want to leave it there. I'm gonna leave a little time for questions. And thank you so much for having me.
Fantastic. Thank you very much, Sarah. We'll do virtual claps, I guess we'll do virtual claps. That was absolutely masterful, really, really interesting, fantastic.
Thank you.
I'm going to give people a little chance to put questions in the chat. If you've got questions, line up in the chat and I'll come to you, or raise your hand or something like that. I've got one or two just before people put in their questions, but one of them is about, so all of these systems look, incredibly bespoke to a specific goal or a specific mission or kind of task. And I was just wondering how much of that is corrected? Like, is everything made, from scratch for every single mission, or how does the recyclability happen? Because you've got some really thoughtful architecture, but it seems like that probably doesn't work for any other mission. Is that right?
Yes and no. Fundamentally, every mission at JPL is basically a prototype, which is why it's being done there versus somewhere else. Every mission is a first of its kind. So there's a lot of really bespoke work that's done both on the process design and the system design and also the spacecraft design for each one. But there is a lot of software and design solutions that are also reused as much as possible from one mission to another. There is also a multi-mission software group that builds and maintains tools that can be used on multiple missions as well. But it's a constant tension between the fundamental novel approach of every new mission and what can be reused from a previous mission. There is always a lot, especially because we're working in space, so having things be reliable is a huge priority, especially whilst using public funding. So whenever possible, something that's been seen to work well previously will be reused. That is a priority when the initial kind of design of a mission.
Fantastic. Leaf, do you want to talk about your question there? You feel free to unmute.
Sure. Yeah. Thanks, Sarah. That was wonderful and mind expanding in various ways. I had two questions, so feel free to answer both or either or neither. So one that was fascinating early on was your meeting. Well, your division between the supposed differences between, if it were, kind of engineer culture, if you like, and the kind of the technologists on the one hand, and then kind of designers and artists on the other. And that's something we encounter a lot in the university. I guess there's obviously this kind of traditional distinction between, say, STEM disciplines and humanities, arts, and social sciences. And I think whilst we acknowledge that, and often there's a lot of in a good way, kind of humility and wanting to work together, we do also, I think, perhaps reify our opinions about what it is that we think that we, as it were, on one side are good at, and what and what the other people are good at, and vice versa. And so it struck me as really fascinating that you took that approach and then said, and we got together and it turned out it really wasn't like that at all. And I wondered if you had any reflections about ways that we might learn from that process and things that we might do, especially in something like the Institute, where we are bringing those folks together. Separately, I just, I loved your diagrams. They were kind of works of art in their own right. And when I think about my hand drawing diagrams, which are always these kind of scrappy little notes of stuff, it put me to shame. But I was fascinated, but I find myself doing that a lot. And then I struggle to try and incorporate that, often in a kind of digital kind of context or vice versa. But I've never been able to get away from or supersede that ability to kind of actually just physically draw things. And it seems to me that that's deeply part of your methodology. So any reflections you have on that too, I'd love to hear.
Drawing either with the hand drawing or then over time then making more formal diagrams is a really important communication tool for me, especially when I'm in a new context and I don't have the domain knowledge yet, or the domain language. Then the drawing really helps to shortcut that, because if you make a drawing and everyone understands the drawing, then you can confirm that what you think you understood is what other people understand as well. For example, when I started on Mars 2020, I had a very short amount of time to do research with all the science teams to understand what was needed. And so and a lot of them were also remote in different parts of the world. I did a live diagramming user interview process where I literally drew immediately in real time everything I was understanding on a huge whiteboard. And then they could point to things and say, did you mean this? And then as it's taking shape, my mental model of what I'm hearing from them, they correct me and then I adjust it. So drawing can be very powerful for bridging those subject matter gaps. in terms of the difference between creative and science or engineering disciplines, I think that the kind of curiosity and intense problem-solving aptitudes, those are the things that really translate across the most for me. And then just getting up to speed, which is simply a matter of time, on domain specifics pertaining to that problem solving, is something that is just a process, and it can be shortcut through drawing. Or what I've found also is that if you like at first I was really preoccupied, like when I was on Europa Clipper, if I didn't have the right terminology, then I wouldn't say anything. Whereas now what I learned, and I had to learn it more quickly on Mars 2020 because I needed to actually come up with a solution very fast for them, and also show them that they could trust me, that I was someone that inspires confidence and like, here, everyone, let's go this way kind of thing. So I just started just finding alternate ways, as long as you're clear and you use clear language. It doesn't have to be even the same terminology the other person would use. And I found that in fact was very powerful.
That's great. Thank you so much.
Yeah.
Fantastic. So there's opportunities for any additional questions. If anybody has them, feel free to raise your hand or pop something in the chat. Sarah, just so the rest of us don't die of jealousy at your job, can you tell us the most frustrating thing in your job? Because it sounds fantastic, but there must be something. And while you're thinking about that, Miriam has an actual.
Sure, and I'll actually stop sharing so that you can, so I'm not this tiny head. Can you, oh, you can see me full size now? Yeah. Or can you see me?
We can see, yeah, we can see, we see the whole group, yeah. Miriam, did you have an actual question?
Or I didn't answer your question yet.
Yeah,
so.
I think it would be better if Sarah maybe answers first. Otherwise it gets a bit confusing.
What's challenging is, I would say the most challenging thing is that it's a large government organization, and the timescale of missions mean that things are done a certain way for years and years and years, and then the next mission comes and wants to do things differently. So innovating and creating changes in ways things are done is it's like moving a big slow government ship, and that has a lot of challenges. I'd say that's probably the most challenging part.
Well, we wouldn't relate to that in the university in the slightest. Miriam, Carrie.
Yeah, I can feel the similarities. My question was about, in a way, what I find really fascinating with your work is that in a way you have to think about having this kind of one-shot situation. So a lot, I mean, I worked a little bit with, I'm a psychologist, but I work with sort of robotics, and we work with software engineering, but it's a lot of trial and error, because you can always have a human in the loop that can correct it. If, you know, the robot falls down, you pick it up and you write the subroutine a bit differently. But for yours, it's kind of, it's much higher risk. So I was wondering, do you think that's a good thing? And in what way does it kind of create a different way of approaching the software or the problem? And would that be a good thing for people maybe sometimes to think that they have one shot and then the money is gone, or then the opportunity is gone, then the thing flies away and doesn't ever pick up any stones from Mars sort of thing? Or is that actually a really stressful and not so helpful thing sometimes?
It does create a lot of pressure, honestly. But there's probably a certain amount of like cannonball polishing that can happen if you've got infinite time to keep iterating and experimenting. On the software side, we can keep doing that because we can update the ground software and even send updates of the flight software to the spacecraft. But the physical hardware is the like one and done part for the most part. There's also a lot of experimentation done on like in a test bed in advance as well. And then there's also usually a duplicate for the smaller spacecraft, like not for Europa Clipper, obviously, because it's enormous, but like for like there's a duplicate Perseverance rover, for example, that's in the test bed right now. So if something happens, we can try and copy what we think happened and physically test it out in this test bed environment. So I think the pressure is good. I think sometimes it can cause people to not have as much leeway to come up with the best option. But I don't know if it's better or not, honestly. I don't have anything to compare to. It does make everyone rally intensely towards the deadline, and causes a lot of creativity to happen. I think if anything, if there were a way to iterate on the next mission a little bit more in closer succession to improve on what we did last time, that would be useful, because really part of the test, like trying out the prototype, is its behavior in space. So we won't really know till we can do that part. But I think you understand why that's a really big challenge from what you've just described. Yeah.
Fantastic. So we are on the hour now. So it would be lovely to be heading for coffee now with Sarah, particularly if we were all in LA. But what we should do is try to maintain some good links. I mean, it's a fascinating area, and it would be great to hear more, to have you back when you've got more to talk about with the results of some missions and things like that. So we'll definitely be staying in touch and trying to make sure that we do maintain links. Thank you very much for your time, and thank you to everybody for joining. And I'm going to let you all go now. We can all do virtual clapping. Sounds good. Thank you very much.
Thanks for having me.
All right.